Hey there, folks. This is your instructor, and let's talk about hypothesis testing. This is the third inference technique that we're learning, right? The first one was point estimation. The second one was confidence intervals. Now, with hypothesis testing, the idea is we want to decide if there's enough evidence to suggest that some null hypothesis is false in favor of some alternative hypothesis. Like, for example, suppose we're told that the mean IQ of a UCSD student is 109, but we sample 70 UCSD students and find a mean IQ of 112. Can we conclude that the 109 number is incorrect? That would be an example of a hypothesis testing, of a hypothesis test in which we were trying to decide something about the mean of a population, namely the mean IQ of the population of UCSD students. Or here's another example. Suppose you're told that 68% of voters approve the federal legalization of marijuana. In order to verify this, you contact 50 voters and find out if they support legalization. So let's find a model describing the number of yeses that you're going to get in your 50 responses. Suppose that 45 out of 50 say yes, that they're in favor of legalization. Does that cause you to doubt what you were told from the outset about the 68%? Finally, what's the minimum number of yeses that you would have to observe in order to cause you to reject the 68% number? Here's the answer to the question. So I asked what model describes the responses. Well, if you are sampling randomly from the population, remember, SRS means a simple random sample. It means each person in the population is just as likely to be picked as each other person. And if the population does indeed adhere to the 68% being in favor of legalization statistic, then our responses will follow a binomial distribution with probability of success being 0.68. Now, you have to make sure that you are sampling randomly from the population. So if you instead went to the campus of, say, UC Santa Cruz and started asking students if they believe in legalization, then you might get a biased response. With regards to the second question, supposing that we got 45 out of our 50 respondents favoring legalization, let's find the probability that we got at least 45. So 45 is one possibility. That seems pretty high. It's higher than 68%, which I guess would correspond to 34 yeses. We got 45. Let's, for the sake of this argument, find the probability that we got any number 45 or greater. And making a, using software, I found the probability of getting a number of 45 or greater in a binomial distribution with n equals 50 trials to be 0.00026. So this is highly unlikely, which means you were probably lied to about that 68% percentage, okay? Because it's super unlikely that you would observe this if that 68% number was correct. So doubt everything, as they say. Now, it's possible that maybe you just got super lucky or unlucky, depending on your opinion, with this particular set of 50 calls. What's the minimum number of yeses that you would have to hear that would cause you to reject the 68% number? So the answer to this question is kind of subjective. It depends how sure you want to be. Like how positive do you have to be? How strong does evidence to the contrary have to be? And for some people, it might be if you observe something that has less than a 5% chance of occurring by random chance, or maybe a 1% or a 0.1%. So it can vary, but the standard level is 5%. This is called a significance level. I'll talk more about it today. So let's find the probability. Let's find the minimum number of yeses that we would have to observe that would cause us to reject that 68% number by plotting a binomial plot and finding the tail that corresponds to 5% area to the right of that tail. And using software, I found that this will happen at 40. So the red area right here is a little bit less than 5%. 40 was the smallest number such that the area to the right was less than 5%. It actually turned out to be 0.04366. So if I observed 40 yeses in this sample of 50 voters, I would start to doubt the 68% number, because there's only a 5%, actually a 4.3% probability of this occurring. So it seems pretty unlikely. Here's another example. Suppose that you have a random variable x and you're told that it has an exponential distribution with rate lambda equals 1/10. And suppose that you observe a value of 20. Would that be considered strange? So in order to answer this question, we want a so-called p-value. This is the probability of observing data at least as extreme as ours, given our beliefs. And we believe that x follows an exponential distribution with rate lambda equals 1/10. So 20 is bigger than what we would expect to get. On average, an exponential distribution with rate lambda equals 1/10 would equal 10, actually, 1/lambda. So 20 is on the large side. So the probability of observing data at least that extreme would be all the area to the right of 20. Making a distribution plot under the assumption that lambda is 1/10 or 0.1, I find that the area to the right of 20 is 0.1353. So this is unlikely, but it's not terribly unlikely. So again, depending on what you consider the appropriate so-called significance level to be, you may conclude that there's not strong enough evidence to conclude that the original belief was wrong. So how strong does the evidence have to be? Well, it turns out that there's a typical threshold of 5%, and this is what is known as the significance level, and we usually denote it with the we usually denote it with the letter alpha. And like I said, it can vary. For example, let's say you're designing pacemakers or airlines, passenger airlines. In that case, you might have a significance level of much less than 5%, like maybe 0.00001%, because if you screw up designing a passenger airline, then a bunch of people can die. Usually, however, we're going to assume a standard significance level of 0.05. So unless otherwise specified, you can usually assume that the significance level is 5%. So all that said, here's how you do hypothesis testing. First, you decide what parameter is trying to be estimated or inferred or tested against. Then you state your null and your alternative hypotheses. In order to proceed, you assume the null hypothesis, then you check the test and the assumptions, compute a statistic, a p-value, and draw a conclusion. Now let me explain each of these steps in more detail. The first step was to decide what's being estimated. So, for example, in the earlier example that I did involving the proportion of voters that favor legalization, we were trying to infer something about the true proportion of voters that favor legalization. That's an example of a proportion. So sometimes you're trying to estimate a proportion. Other times you're trying to estimate a mean, such as with the average IQ of a UCSD student example. The next step in hypothesis testing is to state your null and alternative hypotheses. And this usually looks something like this. You write down what your null hypothesis is, and it's usually of the form mu equals some number. So mu is the population parameter that you're trying to infer. And your null hypothesis is that it's some number that you're told or you suspect, or for whatever reason, is the number that you're performing your hypothesis test against. And then your alternative hypothesis will be that, well, no, it's not equal to that number, or it's less than that number, or it's greater than that number. So depending on the problem at hand, you'll want to do this option or this one or this one. We would sometimes call the first option a two-sided alternative, whilst we might call these second two options one-sided. And in order to determine which one of these you want to do, you usually have to read the problem very carefully. So if we're asking if mu is greater than some possible value. Oh, wait. Oh, crap. There's typos here. The heck is that? Mu sub a. That doesn't even exist. Forget you saw that. Gotta fix this here. Okay. Just wipe that little typo from your memory. The standard way that we write an alternate hypothesis is that mu is not equal to mu naught, or less than, or greater than. And like I said, you usually have to read the problem carefully to figure out which one we're asking. So let's see, do I have an example of that? Yeah, okay, like in the earlier example where I mentioned the average IQ of a UCSD student, maybe you believe that it's actually higher than 109. So if you're told that it's equal to 109 and you believe that it might be higher than 109, then this would be the appropriate alternate hypothesis. That is. Now, as a general rule, the null hypothesis is the case that there's no effect, i.e. nothing to see here, and it's the boring option. As a researcher, you usually hope to reject the null hypothesis because that entails finding a statistically significant effect. In order to proceed with hypothesis testing, you assume that the null hypothesis is true. Now, this can be kind of weird, especially if it's not true. So you're assuming something that is quite possibly likely to not be true, but that's the point. You're later on going to derive some contradiction, or at least derive some results that are highly unlikely under this assumption. So the next step is to choose the test. Now, I'm going to talk later about the various tests. There's a few different ones, such as the one proportion Z test and the one sample T test and so forth. So more on that later. I'm also going to talk about the corresponding assumptions that go with the tests. But once you know about the tests and their assumptions, you need to check those assumptions in order to proceed. And sometimes the assumptions, which generally have to do with like your sample size or with the shape of the population distribution, like is the population distribution normal, for example, and are your samples random or appropriately random? So those are the assumptions that we're going to check later. And often in practice, it's not clear as to whether they are satisfied. So this can sometimes be a difficult step to determine conclusively. In theory, if the assumptions are not satisfied, you're supposed to stop with the test. You're not supposed to proceed. However, in practice, in this class, you often will still proceed, but just make sure to make a note of the fact that the assumptions are not or might not be satisfied. So that way, we at least know that you know that the assumptions are not necessarily satisfied. So anyway, we'll get to all that later. The next step in hypothesis testing is to compute your test statistic. So this is some single number, and it follows some known distribution, at least under the assumptions of the null hypothesis. And the test, which, as I said, we'll talk more about later. Once you know your test statistic, you can compute a p-value. So p-values are probabilities. That's what the p stands for. And it's the probability of obtaining data at least as extreme as what was observed given the null hypothesis. Finally, you make a conclusion, which is that you either reject or fail to reject the null hypothesis. And this depends on whether the p-value falls below the significance level. So, for example, if the significance level is 5% and you end up with a p-value of 4%, that means that there was only a 4% probability of observing data at least as extreme as what you observed under the assumption of the null hypothesis and the test. Since that falls below your significance level of 5%, you conclude that the null hypothesis is untrue, or at least unlikely to be true, and you reject it. Just because you fail to reject the null hypothesis, that does not prove that there's no effect. It just means that you didn't have good enough evidence. It might mean, for example, that you got unlucky. It might mean that you need to redo the test, but with a greater sample size, for example. Like if we go back up a bit to my earlier example here, I found a p-value of 13%. So it's unlikely. The prior could have been wrong in this case. We just didn't get strong enough evidence to overturn it. Another note about our conclusion. Hypothesis testing doesn't really give you very much information. For example, it doesn't tell us what the true parameter is. It just tells us that the null hypothesis is probably wrong. And even if we do reject the null hypothesis, every once in a while, this can happen just due to random chance. And in fact, there's a name for this type of error. It's called a type 1 error, and we're going to talk about those the next lecture. So it's possible that you end up wrongly rejecting the null hypothesis, but just due to random fluctuations. So let's do an example of hypothesis testing with the heights of males in our class. I looked up the average height of a modern human male, and I found that it was 67.4 inches. I sampled 10 males from our class using class survey data. In fact, here, you can even see the code for that if you want. I just picked 10 males randomly from our class. These were the 10 heights that I got. The question is, can we conclude that the average height of males in our class is greater than 67.4 inches? So here's the answer. The parameter that we're trying to estimate is the mean height of males in our class. The sample in this case is the 10 students that were selected from the class. So the null hypothesis is going to be that males in our class have the same height distribution as the world does. That is to say that the average height of males in our class is 67.4 inches. If you read the question carefully, you'll see that I'm asking for a one-sided hypothesis test because the key word there is greater. Hence, my alternate hypothesis is that the mean height of males in our class is greater than 67.4 inches. We'll now assume the null hypothesis in order to proceed with the test. The test that I'm going to use is called the one sample t-test, but I'm going to talk about this later. So there's a few aspects to this example that aren't going to totally make sense. And that's just because we're going to get to those in a later lecture. So just bear with me for that. And I'll also talk about the assumptions for the t-test. Using the data in my sample, I compute the mean and the standard deviation. The mean was 68.2 inches, so taller than the global average. Standard deviation was 3.55, and as it turns out, those are what we need in order to compute our test statistic. So again, this is something I haven't taught you yet. We'll get to that, but just FYI, here's how we would do it in order to perform this test. We're going to use this. We use this formula for the test statistic. We take the sample mean, divide by the proposed population mean under that is the population mean under the assumption of the null hypothesis, divide by the sample standard deviation quantity divided by the square root of the number in our sample. In this case, those numbers come out to be 68.2 minus 67.4 divided by 3.5 itself divided by square root of 10, which is approximately 0.71. And as you'll see when we talk about the t-distribution, this test statistic is supposed to have a t-distribution with 9 degrees of freedom. So don't worry about that yet, but here's what that distribution looks like. The probability of observing data at least as extreme as what we observed is the area to the right of 0.71 on this distribution, which via software I find to be 0.2478. Hence, our p-value is 0.2478. Since this is not less than 0.05, we failed to reject the null hypothesis, right? We did not have strong enough evidence to conclude that the males in our class are taller than the average modern human male height, at least based on this particular sample. Notice that I used the significance level of 0.05 by default because nowhere in the problem did it suggest anything to the contrary. Conceivably, you might be asked to use different significance levels, but in this case, since there wasn't any mention of any significance level, you just defaulted to using 0.05. So yeah, we failed to reject. Does this mean that it's not true that males in our class are taller than the global average? No, it does not mean that. In fact, FYI, I went and computed the average height of the males in our class, and it is taller than the global average. We just weren't able to prove that using this particular sample of 10 students. Although the fact that we got this p-value, I mean, It's not super likely. Yeah, you can't really say much when you get a p-value of 0.04. That could very well happen by chance. But anyway, you can go check the class survey data and find the average height in the class if you want. I think it was something like 68.5 or like 68 point something inches. So it is in fact taller than the global average, although a little bit shorter than the US average. Okay, anyway, so that's the end of this example, and that's the end of this hypothesis testing lecture. So that's it, folks. Thanks for watching. Regarding the second example, it was where you know for certain that this random number has an exponential distribution, but you don't know for certain the rate, but you're told that the rate is 1/10. Then we found the probability of getting a number as extreme as 20. Notice that if the rate is 1/10, then a typical value of this distribution would be 10. 20 is to the right of 10, so the probability of getting a value as extreme as 20 is the probability that x is greater than or equal to 20. Ended up being 13%, 13.5%. So I now have a follow-up question to this problem. Is 0.5 a strange value to get? Again, where we are told that lambda equals 0.1. Yes or no, folks? In order to answer this question, I assume that lambda is 0.1. Yes or no button. Not getting a lot of responses. In order to answer this, and this is, with this same example, in order to answer the question of whether 0.5 is a strange value, we do assume what we've been told. So yes, for now. And what you do is you assume it, and then you see what conclusions can be drawn. Later, we would see that this is the so-called null hypothesis. Okay, so we're going to assume that lambda is 0.1 for the remainder of this problem. In order to determine if 0.5 is a strange value, let's see. Yes or no? We want to find the probability that x is equal to 0.5. Yes or no, folks? Okay, good. Yeah, most people are saying no. In fact, this is definitely 0. Because x is continuous. But even if it wasn't, that still wouldn't be what we want to find. Speaking of continuous densities, Did any of you watch the 3 blue, 1 brown video where he talks about this? Oh, cool. At least one person did. Yeah, he does a great explanation, Grant Sanderson, the author of those videos, as to why a probability such as this would be 0. So I really recommend that you all watch those. That it would be the second of the 2 3 blue, 1 brown videos that I posted in today's video. Okay, fine. Yes or no? We want to find then probability that x is greater than 0.5. Yes or no to this one?
Professor, what categorizes a strange value? I missed that part.
Yeah, it's kind of subjective, but let's say something that something for which the probability of observing it or something even more extreme is less than 5%. Yeah, so that's a good question. That's the tricky thing here. We usually set our cutoff at 5%, and I'll explain the event or something more extreme right now, actually. So the reason that this one is no is the same reason we went to the right of 20 before, and 20 was to the right of 10. Well, remember, a typical value in this distribution is 10. That's the mean. 0.5 is now to the left. So we now want probability to the left of this extreme value. So a more extreme value than x equals 0.5 would be x less than 0.5. Okay, so we want the probability that x is less than 0.5. And here, you know what, I actually already did this calculation. So here we go. The probability that x is less than or equal, we can include 0.5 if we want, will be the integral from 0 to 0.5 of the exponential density. And it ends up being 0.0487, which is the area in this little sliver right here. So you can conclude, depending on your significance level, that 0.5 is a strange value. So to address Andres, we observed something which happens with less, I'm speaking a bit imprecisely, it roughly happens with less than 5% probability, which is unlikely. So this would be strange. William?
I'm just confused because I'm not sure what the null hypothesis is exactly identifying as true with this example, because you said that 0.1 was the null hypothesis, which didn't make sense because that's lambda, not x.
Yeah, right. So the null hypothesis is that lambda is 0.1. Assuming it to be true, we found that we observed a very rare event. But that's not likely. I mean, what are the chances that the very first time we do this experiment, we find a value that is so rare, that is so unlikely? It causes us to doubt our hypothesis about lambda. And with other hypothesis testing problems, you are, again, often assuming something about a parameter, not about the random variable.
Oh, okay. Got it.
Mhm. And let's see, Minjin asked about one tail and two tail. And yes, we do care about one tail and two tail tests. I'll get more into those later. Part of the way that you can tell whether you want a one tail or two tail test is you have to read the question carefully. Like, for example, in the marijuana problem, I said in favor of something higher, no pun intended, but higher than 68%. And here, let's go to the next example, because I think that will help illustrate this as well. And this is the main thing I wanted to do today, which is a hummingbird example. So I looked this up, and the wingspans of broad-tailed hummingbirds are normally distributed. Well, so that's not the part that I looked up. Forget that I looked anything up. So the wingspans of broad-tailed hummingbirds are normally distributed, and their standard deviation is known to be 2 centimeters. And you are told that their average wingspan is 15 centimeters. But you're told this by a questionable source, so we're not totally sure about whether that 15 centimeter average is accurate or not. But we do know the standard deviation. Never mind how it's a bit strange that you would know the standard deviation and not the mean. We'll address that issue later in the class. For now, just take it to be the case. First question, would you trust this value of the mean wingspan of a hummingbird if you found a hummingbird and you measured its wingspan to be 13 centimeters? Okay. Yes or no? In order to answer this question, I should assume going forward in the problem that mu equals 15. Yes or no, folks? Good, yes. Yeah, this is how. Now, this may be false, and we may end up deriving an unlikely result or consequence, but in order to proceed, we assume that it is true. Okay, good. So how about let's let x be the wingspan of a single random hummingbird. And in fact, maybe I should have added the word random. All right, like if you went and found the biggest hummingbird you could find, then this analysis might not work. So we'll just add the word random right here. So let's let x be the wingspan of a single random hummingbird. Yes or no? Our p-value for this experiment will be the probability that x is greater than 13. Yes or no? Okay, good. Yeah, this one's a no. No, because 13 is less than what we were told. So we want the probability of events more extreme than what we observed. Since 13 is less than 15, this means that we want the probability of observing values of less than 13. Okay. So since we're assuming that mu is equal to 15, and it's known that the wingspans follow a normal distribution, like most biological variables, we know that X follows a normal distribution with mean 15 and standard deviation 2, under the assumption of the null hypothesis. That is, under the assumption that what we were told is correct. Okay, so our p-value is probability that X is less than 13. And I actually did this on our studio. And I got 15.86553%. Okay. This is not strong evidence that we were missing for. So now let me address the second part of this hummingbird question, which is, suppose we now go and find 9 hummingbirds, 9 different random hummingbirds, and their average wingspan was also 13. So let's see how the analysis changes at this point. Okay, so now how about we let x sub 1 through x sub 9 be the wingspans of 9 random hummingbirds. Let x bar be their mean. Yes or no? X bar has a normal distribution with mean 15 and standard deviation 2. Yes or no? Good. Okay, yeah, you guys are getting this one correct. Good. Oh, and I see Nathaniel asked me a question about the first part. He asked if we could have used that 13 is 1 standard deviation away from 15, and yes, that would have been a shortcut. In fact, so you could have even used the 68, 95, 99.7 rule if you wanted. Let's see, what does that leave? Yeah, it leaves about 16% on either end, and sure enough, we got about 16%. So yeah, that would have been a shortcut to do that part of the question. Can someone tell me what the standard deviation here should be in this equation? It's not 2. What should it be? Ryan?
Isn't it 2 divided by square root of 9, which is 3?
Ah, good. Yeah. All right. It's 2 divided by the square root of 9. Not 2 over 9, not 2, but 2 over square root 9. Okay. So I'll just put a 3. Cool. So now our p-value is the probability that x bar is less than 13. Again, because 13 is less than 15, and I did this in R as well. And we got 0.0013. So like 0.1%, less than 1%, more like 0.1%. So this is a highly unlikely outcome under the assumptions. So it gives us cause to doubt the reported mean. Okay. Any questions on this example? Let me just ask one quick little question about the evidence. So, like Andres was asking about how do we know whether we should discount what we've been told or not? The standard threshold is 5%. That's called the significance level, or alpha. Yes or no, folks? Increasing alpha makes it more likely that we detect an effect in whatever experiment that we're running. Yes or no, folks? Yeah, because the let's see, like the smaller alpha is, the stronger the evidence that we need. If alpha is big, that makes it easier to disregard our null hypothesis in favor of concluding that there is an effect. So the way things usually go, the null hypothesis means there's no effect, and you hope to reject it. Certainly as a scientist, like you hope to get a result. Getting a null result is pretty boring. Arguably, it's one of the main causes of the replication crisis is because too many scientists and researchers don't report their null results. They all report the times they rejected it. They don't report all the times they failed to reject it. So yeah, maybe they need to change their significance level or whatever it is. If you increase it, you're more likely to reject. You're also more likely to wrongly reject, as we'll talk about in the next lecture. So that's it for today, folks. Thanks for watching. I'll see you all on Wednesday, and I'll hang out to answer any questions.